Hello, everybody. I am just going to do a video here for the Chapter 7 notes. I have to switch up my plans a little bit from normal for my in-person section. We are going to deal with Chapter 7, Probability Living with the Odds. So I'm going to go through the notes here just like I normally would in class for those of you that have me in person. For those of you that are online, this should be pretty much how it's been before. So fundamentals of probability is going to be the basis of chapter 7, which is the likelihood for an event to occur. Probability is the chance that an event will occur. Probability experiment is the process by which we get the results of whether or not an event will happen or not. The outcome is the result of the experiment. And the event can be a collection of one or more desired outcomes. So, for example, if we were going to roll a dice from 1 to 6 and say we wanted to know the likelihood of rolling a 2 or a 3, 2 or 3 are both outcomes. And there are two events here that can occur. There's only going to be one outcome when we roll the dice, but it can be either the event that we get a 2 or that we get a 3. The notation here is going to be very important. P of A is written as probability of event A occurring. So P of A is often written as a decimal. Between 0 and 1. 0 means it's impossible. It ain't going to happen. 1 means it's certain that it will happen. It will always happen. And then anything in between as well. There are three types of probabilities that are out there. The theoretical probability is assuming that we have infinitely many trials and we can perform a probability experiment over and over and over again. The relative frequency is based on repeating the experiment over and over, called empirical probability. This is what actually occurred. In an experiment. And relative frequencies are based on writing a decimal as well. And there's subjective probabilities based on experience or intuition based on numerous other factors. So for example, if you toss a quarter, the theoretical probability of getting ahead, if we did this infinitely many times, is going to be 0.50 or 50%. But if we toss a quarter 100 times and it lands up heads 43 times, the relative frequency probability of getting ahead is going to be 43 favorable outcomes that out of 365 days, or about 0.337. From there, sometimes it's easier to figure out probabilities of the event not occurring. So think the keyword here is not. So instead of figuring out what are the chances of rolling a 2 or a 3, we could also figure out what the chances of not rolling a 2 or a 3 would be. So going back to the example, the probability that the sock we get out of the drawer is not black is going to be 1 minus the probability of getting a black sock, which would be 10 out of, there are 28 in the drawer. To add or subtract fractions, you need common denominators. So that is really 18 over 28. Which will be 0.643 approximately. 40% of students purchase a hardback book according to a publisher randomly selected. The probability that they do not purchase a hardback book, 1 minus 40%. Now 1, as you might know, is the same thing as 100%, minus 40%, or 1 minus 0.40, which will be 0.60, or 60%. So again, just working out different examples here with probability. From there, this gets us into odds, which is the ratio or fraction of the probability that a particular event will occur to that probability not occurring. It's often used in a lot of gambling devices. So the lottery, for example, will show your odds of winning. If you bet on horse races or anything like that, they present your chances of winning in terms of odds. So for example, if we have that sock drawer again, one sock is selected, what are the odds for getting a black sock? So keep in mind it's always favorable to unfavorable. So 10 black socks are good in this case for part A. There are 18 that are not black that we don't want. We can reduce this down. Each of those are even, so we can divide them by 2. So odds of 5 to 9. For part B, odds against, literally what you did in A, but reversed. So the odds there would be 9 to 5. From there, we can combine probabilities together, which can get a little interesting. Either or either or probabilities is going to involve addition, as long as they are mutually exclusive, or what that means can't happen at the same time. If, however, they can occur at the same time, then you have to subtract the probability of getting both of those together. So 10 black stocks, 6 navy, 12 white. Probability that it is navy or white. So to do that, there are 6 navy and 12 white that we can add together over 28 total socks in the drawer. So 18 over 28. Be about 0.643. And I just rounded to 3 decimals. Probability that it is black or white would be 10 plus 22, 10 plus 12 white over 28, which will give you 22 total. I was getting ahead of myself there a little bit. Typing that into a calculator, you will get 0.786 when we round to 3 decimals. We can do this with a deck of cards. The probability that you get a king out of a deck of cards, there are 4 kings out of 52 cards in a deck. Getting a queen is the same probability. Getting a diamond, there are 13 diamonds out of 52, which will actually reduce to 1/4. These first two will actually reduce to 1/13. Getting a red card, there are 26 of them out of 52, reduces to 1/2. Probability that you get a king or a diamond. There are 4 kings in the deck, plus 13 diamonds. However, it is possible to get the king of diamonds at the same time. We don't want to include that twice, so subtract 1, all over 52, which will give us 16 over 52, which is 8 over 26, which is 4 over 13. For F, getting a king or a queen, 4 kings, 4 queens, so 8 in total out of 52. You can't get both a king and a queen at the same time when you pull a card out of the deck. And then for G, probability of getting a king, there are 4 of them, or a red card, there's 26 of those. But you can get a red king, which would be either the king of diamonds or the king of hearts. So 2 of those we would have to subtract, which will give you 28 over 52. We can divide each of those by 2, so 14 over 26, or 7 over 13. So in other words, getting the king or the diamond, those are not mutually exclusive events. You can have both of those occur at the same time. The king or queen, those are mutually exclusive because you can't have those occurring together at the same time. And is the other kind of probability. If the events are independent of each other, it's going to involve multiplying. Independent means the result of the first event, so result from 1 doesn't affect 2. So then with that in mind, if the result of the first one will change what happens in the second one, you have to take that into consideration. So then it's going to be probability of the second thing happening given that the first one occurs. So an example here, you select a card from a deck, replace it and select another card. Probability that the first card was a diamond. So there are 13 diamonds in the deck out of 52. We're putting that back in the deck, so we're still going to have 52 cards. The second was a heart, would also be 13 of those. Each of those reduced to 1/4. Multiplying fractions, that will be 1/16. For part B, select 2 cards from the deck, not replacing this time. Probability that you get a diamond on the first card, so 13/52. Not replacing it the second time, so 51. A heart on the second card, there's still 13 of those in the deck. So that will be 169 over 2,652. So if you select 2 cards, the probability that they're both diamonds would be 13/52 times 12/51, because we're not replacing it. Since I'm running out of room, if you select 5 cards, 13/52 times 12/51 times 11/50 times 10/49 times 9 of them out of the 48 that would be left. Multiplying straight across for all the fractions will give you the final probability. Another example, going back to the sock drawer. 2 socks are selected, probability that the first one is navy. So 6 of those out of 28. The second one is white. We're not replacing it, so take 1 away. There are 12 white socks in the drawer. We can't get both at the same time, so we don't have to worry about that. 2 socks are selected, probability that the first one is white. So 12/28 times second one being navy, 6 out of 27. And then for C, probability that they're both black, 10/28 for the first one. And now we take 1 black out of it, 9 out of 1 less 27. Again, multiplying those out will give you the final probabilities. We can do this with percentages as well. So probability that the first one rented a book, so 35%. Second one bought an ebook, 25%. Again, the events are independent. Probability that they both bought a hardback book is going to be 0.40 times 0.40 again. If they're selected for C, that neither of them bought an ebook. So not an ebook is going to be 75% of the publisher's audience. So think 0.75 times 0.75. Because again, 75% is the complement of 25%. If 4 students are selected, what is the probability that they all rented a book? So 0.35 times 0.35 times 0.35 times 0.35. Or if you'd like a shortcut, 0.35 to the 4th power will get you there. But the reason that we have probability is so that we can assess risk. Often occurs in real life situations such as accident rates for insurance companies, death rates, life expectancy types of calculations. Rates are typically expressed as ratios or fractions. So an example here of using some real data. Table below shows the 2019 leading cause of death in the US, assuming that the US population is 330 million. What is the risk that someone dies in an accident? So we will get the value from the table, 173,000, over the total population, 330 million. Each of these numbers have 3 zeros at the end, so we can just get rid of 3 zeros out of each number. So 173 divided by 330,000 is going to give us 0.000524, or as a percentage, 0.0524%. You'll have to either move the decimal 2 places or multiply that number by 100. Again, you can find underlying reasons behind spikes in these types of things. Graphically, it's much easier to see. But just some things to think about. In early 2021, the US temporarily halted use of one particular vaccine against COVID-19 due to the discovery that approximately 6 in 1 million people were experiencing severe and sometimes fatal blood clots. Around the same time, data suggested that unvaccinated people in communities without substantial herd immunity had about a 1 in 10 chance of contracting COVID-19, and that about 1% of infected individuals would die from the disease. Did the decision to halt the vaccine save lives? Well, you had a 1 in 10 chance of contracting it, so 10%. 1% of these people were expected to die. So probability of 0.001. You have 6 divided by a million up here. So 6 divided by 1 mil, 0.000006. Actually, 5 zeros. So did the decision to halt the vaccine save lives? No. Because the probability without it, so probability of unvax, dying is greater than the probability of vaccinated dying. Another common one would be shark attacks. I'll let you try this one out on your own here. Another one could be surveys involving terrorism. We tend to be more fearful in situations in which we lack control. That's why many people fear flying more than driving. The seemingly random nature of terrorist attacks plays to this fear since we have no control for when or where they will occur. Second factor, potential harm to a large number of people at once. And a third factor is that's because the media covers this any chance they can. So that's why surveys consistently show that terrorism ranks near the top of our fears. For example, human psychology can contribute to the answer or some other underlying why we get the results that we do. Statistics is the art of being able to answer these kinds of questions by giving explanations in the real world. Basically, statistics tries to make the data make sense or give a reason why the data occurs. The psychological or other factors may or may not lead to actual truth here, just because even though terrorism is constantly at the top of our list of fears, it's not as likely to occur as, say, car crashes or injury by firearms. So the point being, perception can manipulate surveys, it can manipulate data. So you really have to look at what is occurring behind the scenes. Often, if you look at the context of the situation, that will help you determine if our probability makes sense or not. So this is the chapter on probability, chapter 7. Please let me know if you have any questions. You can email me at any time, and I will see you all next time. Have a good one, everybody.